So I wanted first to thank the scientific committee, in particular Nizar Touzi, Nicole El-Karoui, and also our colleagues from Bielefeld, in particular Frank Riedel and Giorgio Ferrari. I had visited Bielefeld University upon their invitation before the COVID crisis. I thank also Mirjana with a special thought for the team of the same. So I will speak about European and American options, the pricing of European and American options in a nonlinear incomplete market with default. This talk is based on two works, two papers, also with co-authors, Mirjana and Agnès Sulem. So, we consider a market with imperfections. More precisely, a market with default. Also a nonlinear market, that is, the dynamics of the wealth are nonlinear. The market is incomplete, and our goal is to study the superhedging of European and American options. More precisely, the model is as follows. We let omega GP be a complete probability space. Let W be a one-dimensional Brownian motion. The default time is a random variable, theta. We denote by n the default jump process. Nt is equal to the indicator of theta smaller than t. We denote also by g the filtration associated with W and n. And we make the assumption that W is a G Brownian motion. Recall that we have a G martingale representation theorem with W and M. M is the default martingale. I will define it in the next slide. So we make the assumption that the G predictable compensator of NT is absolutely continuous with respect to the Lebesgue measure, is the integral of lambda s ds, and lambda s, the process lambda s, is called the intensity process and is supposed to be bounded. And note that it vanishes after the default time theta. So the compensated martingale of NT is given by MT equal to NT minus the integral of lambda s ds. Denote it here. Let capital T strictly greater than 0. We denote by H2 the set of predictable processes Z, such that the expectation of the integral of the square of Zt with respect to dt is finite. And we denote by H2 lambda the set of predictable processes K, such that the expectation of the integral of K2 square lambda t dt is finite. So the market contains only one risky asset, which dynamics is as follows. So here mu t is predictable, is G predictable and bounded. Sigma t, the volatility is also, and beta t, which is the size here of the jump, is also predictable and bounded and strictly greater than -1, so that the price process remains non-negative, since S0 is strictly and positive, actually. S0 is strictly greater than 0. And to simplify the presentation, I will suppose that the volatility is equal here to 0. So the dynamic of the price is just given. Here you have 1 plus beta t dmt. The investor, consider an investor with an initial wealth X, and he can invest his wealth in the risky asset and in a non-risky asset, and we denote by ZT the amount invested in he invests in the risky asset at time t. Z here is a process belonging to H2. And we denote by Vxz the value of the portfolio at time t. Note that there are two sources of risk, W and M, but only one risky asset, which is available for investment. So the market will be incomplete, as always, I will explain in the next slide. So here the dynamics of the wealth is supposed to be nonlinear. Well, more precisely, it is as follows, that dvt is equal to f of t vt zt dt minus zt multiplied by dwt plus beta t dmt. Note that this is the martingale here, which appears in the dynamics of the price process. Pardon?
Is the minus sign correct?
Ah, yes, minus, sorry. Like this is backward, and F here is a Lipschitz driver. So here is the dynamics of the wealth with initial wealth X. In the classical case, the driver F corresponds F of VTZT is simply equal to minus RT, the interest rate RT, VT, minus theta T ZT, where theta T here is equal, is the risk premium, which is, since sigma T is equal to 1, it is just equal to mu minus R. So there is also an example, the example of funding constraints, that is the borrowing rate R is strictly greater, greater than the lending rate R, and different. And in this case, the driver F is of this form, so it is nonlinear with respect to V and Z. Well, it had been studied by different authors, and more recently by Krippe to study the nonlinear pricing of CVAs in a market with default. Another example is given by the case when there is a repo market in the market with default, on which the risky asset is traded. In this case, the driver F is of this form. BT is the borrowing repo rate here, and LT corresponds to the lending repo rate. So also it's a driver which is nonlinear with respect to Z. We have also another example of a large seller whose strategy impacts, in particular, the default intensity. Well, it's a bit more complicated to write it precisely, but we had done it in a paper, in a previous paper. So recall the pricing in a complete market, in a complete nonlinear market. We consider, donc that was in our work with El Karoui and Peng. Here the Brownian, the filtration is the Brownian filtration, that is F equal to the filtration associated to W. And the risky asset, the price of the risky asset, follows this dynamic. Here again, sigma is equal to 1. And we consider a European option with maturity capital T and payoff eta. Then we know, by results on barcode equations, that there exists a unique pair of processes, adapted processes, xz, square integrable, such that minus dx is equal to f of xtz dt minus zt dw, with terminal condition xt is equal to eta. And so here we recognize the dynamics, the dynamics of the Wells process, because in this case this corresponds to the dynamic of the Wells process. And so x is equal to the value of the Wells associated with initial Wells x0 and strategy z. So our European option with payoff eta is replicable, and x0, which is equal to the initial wealth of the replicating portfolio, is the hedging price here for the seller. This leads to a F nonlinear pricing system, which was introduced, which we introduced with Nicole in 1997, which to each pair terminal time t and payoff eta associate the process x associated with terminal time t and terminal condition eta. And the solution actually of this backward. Well, this we had noted that this nonlinear pricing system satisfies a monotonicity property with respect to the payoff eta, well, even a strict monotonicity property by the strict comparison theorem, a consistency property, the no arbitrage property, and also it is non-negative with respect to eta when the driver computed at 0, 0 is greater or equal to 0. And also it's convex with respect to the payoff eta for convex f. This operator was then denoted by Randy f and called f expectation by Peng, with the same terminology, financial terminology for properties. So this is exactly the same operator. Here, terminal time is here. So it's exactly the same. And if here in this work, we will suppose that f computed at 0, 0 is equal to 0, so that the price of the option with payoff 0 is equal to 0. And we have also by this the non-negative property even of the or non-linear pricing system, and from which we derive that there is absence of arbitrage in our market. Well, note that the buyer's price in this complete nonlinear market is by symmetry. Well, it is symmetric. We are denoted by tilde x 0. It is equal to the opposite of the seller's price of the option with payoff minus eta, and hence it is equal to the nonlinear expectation associated with f associated with terminal payoff equal to minus eta. And just a remark, the process z tilde, which is tilde z, which is associated with x tilde, that is x tilde, z tilde, is the solution of the backward, of this backward with terminal condition minus eta. It corresponds to the hedging strategy for the buyer. Well, here our nonlinear market is incomplete. Here our filtration G is a big filtration generated associated with W and N. Indeed, let eta be a GT square integrable variable. It might not be possible to find a strategy initial well X and risky asset strategy Z such that the associate wealth at the terminal time capital T is equal to the payoff eta. In other words, well, here I have just written the dynamics of the wealth. So there does not necessarily exist a pair of adapted process VZ satisfying this dynamics with terminal condition equal to the payoff. So I will just, yes. So. However, by the G martingale representation with respect to W and M, there exists a unique triple YZK, which are square integrable and adapted, solution of the BSD with default, that is, driven by W and by M, with here the same driver F. But in general, the process K is not equal to Z, to Z beta. So this dynamics is not the same as this one. It does not correspond, why, to the value of a portfolio. So the our option, or European option, is not necessarily replicable in our market. So I just introduced the classical notation. If YZK is a solution of the G BSD, the one I have introduced, we set E round F at time S associated with terminal time capital T and terminal condition eta is equal to YS, the solution, the first coordinate of the solution. And it is called, as usual, with using Peng's terminology, F conditional expectation of eta under the primitive probability P. So it defines a possible price, but in general, as we have seen before, there is no hedging strategy, except if K is equal to Z beta.
Negative.
Sorry?
Should be negative. Equal. Equal.
Ah, no, not except. I don't know why I had made the correction, yes. But since k is not equal to z beta. Sorry. So we define as usual the seller's superhedging price at time 0. As usual, it's the infimum of the initial wealth, which allows to construct a risky asset strategy such that the associated wealth at time capital T is greater or equal to the payoff theta. So the question is, do we have a dual representation formula for this price? Recall the classical linear incomplete case. So to simplify, up to discounting, we may suppose that the interest at R is equal to 0. So in this case, the driver is F is just given by minus mu T multiplied by Z. Well, this is just the classical definition of a martingale probability measure. And we have a dual representation of the seller's superhedging price. That is, the superhedge V0 is equal to the supremum over all martingale probabilities R belonging to P round P. Round P is a set of martingale probability measures here of the expectation under R of eta. And recall just a sketch of the proof. There is one inequality which is very simple to obtain by using the martingale probability of the wealth processes under each martingale probability R. For the other inequality, it's more difficult, and the proof relies on the optional decomposition theorem, well, in the linear case, which says that if a process YT is a CAD-lag supermartingale under all martingale probabilities, then there exists a process Z, which is in our case a strategy, a risky asset strategy, and a CAD-lag non-decreasing optional process H, which is equal to 0 at time 0, such that YT is equal to the value of the wealth associated with initial wealth Y0 and strategy Z minus HT. So the question is, what is the analogous of martingale probability measures in the case when F is nonlinear? First, to do this, we define the notion of nonlinear F expectation under Q. Well, this is not a new notion, but well, in this model, maybe, I don't know, for Q equivalent to P, the probability Q equivalent to P. So from the G martingale representation theorem, we can represent its density process zeta t as follows, that is, as an exponential martingale process with coefficient since alpha denoted by alpha t for the Brownian motion and ut for the martingale, the default martingale. So there are J predictable process, nu is strictly greater than -1, so that zeta is strictly, remains strictly positive. And we know that by Kirsanov theorem, WQ defined as W minus the integral of alpha is a Brownian motion under Q, and MQ defined as M minus the integral of nu s lambda s is a martingale under Q. So, and it is quite easy to show that we have a Q martingale representation of Q martingales with respect to the Q Brownian motion WQ and to the Q martingale MQ. So we can thus consider BSDs under Q driven by WQ and MQ. So more precisely, let XZK be a triple of adapted processes, square integrable, solution, which is the unique solution of the following QBSD with driver F and driven by the Q Brownian motion WQ and the Q martingale MQ with terminal condition eta. We can call Q pricing system or F expectation under Q, denoted by round EQ, or more simply like this, the operator defined for each eta, GT measurable, by E round Q at time S of eta is equal to XS. The solution, the first coordinate of this solution. Well, we recall the definition, well, it's just given under Q, but it's the same as before. A process Y is said to be a strong round EQ supermartingale or round E supermartingale under Q if for all stopping time tau sigma with tau smaller or equal to sigma, we have this inequality. Well, and similarly, we can define the notion of strong E round Q martingale. So the question was, what is the analogous of martingale probabilities in our nonlinear case? So we will define E round martingale probability measures as follows. A probability Q equivalent to P is called a round martingale probability measure if all the Wells processes are round martingale under Q. And we denote by round Q the set of all round E martingale probability measures. We can show that Q is a near-round martingale probability if and only if its density zeta is an exponential martingale of the following form. And here, this is the coefficient alpha t, which depends of this one, ut. So it is, we see that the density is parameterized by this coefficient nu, which is only a predictable process, and satisfies the constraint nu strictly greater than -1, so that again zeta is strictly positive. Nu can be interpreted financially as a risk premium orthogonal to the market. Well, we note that P, the primitive probability, belongs to round Q, is a near-round martingale probability. It just corresponds to the case nu equal to 0. And also, we have that this characterization, that is Q belongs to round Q, is a near-round martingale probability, if and only if W plus the integral of beta S with respect to dms is a Q martingale. And recall that this is the martingale which appears here in the dynamics of the price process and also in the dynamics of the Wells. So we see that round Q does not depend on F, actually. And we have the dual representation formula of the seller's price. which is that under an appropriate integrability condition on eta, which is, for example, satisfied by the call option, we have that the superhedging price V0 is finite, and that V0 is equal to the supremum over all E-round-martingale probabilities Q of the nonlinear expectation of eta, more precisely, the round EQ expectation of eta. Well, the sketch, let us see the sketch of the proof of this result. As in the linear case, this inequality is easy. It follows from the definition of martingale, an E-round martingale probability measure, which is that all the wells are E-round Q martingales, which is, well, we derive this quite easily. The other, to show the other inequality, we first show the following nonlinear optional decomposition theorem, which generalizes the linear decomposition, the previous linear decomposition, which is that if y is a strong, is square integrable under all E-round martingale probabilities, if y is a strong E-round Q supermartingale under all Q belonging to round Q, then there exists a process Z in H2 and a non-decreasing optional process, CAD lag, H, equal to 0 at time 0, such that YT can be represented as follows. That is, it's dynamic. Here you have the driver F, and here you have the integral of Z with respect to O martingale W plus beta DMS, which is a martingale under all E-round probability measures, or F probability measures, as we had seen, minus HT. Here we recognize the dynamics of the wells, but however, this is not, contrary to the linear case, this is not the value of a Wells process because of the nonlinearity. So let us see quickly the end of the proof of the dual representation. We introduce to do this the following dual problem, which the value function at time S is defined as the essential supremum over all E-round or F martingale probabilities Q of the Q conditional the Q round E conditional expectation at time S of the payoff eta. And so we had, with this notation, it remains to show that x0 is greater or equal to v0. To do this, we first show that X is a strong E-round Q supermartingale for all F martingale probability. Well, note that at time capital T, xt is equal to eta. Furthermore, it is the minimal process which satisfies this condition. So, since we have this property for xt, we can apply the optional Randy decomposition theorem, which is that there exists a process Z in H2, an optional non-decreasing process H, such that xt can be decomposed as follows. So we see we have minus ht. Note that if h, in the case where h is identical to 0, well, x is just the value of a portfolio associated with x0 and z. but with H, it's not the case. But since H is non-decreasing, equal to 0 at time 0, we can apply the comparison theorem for forward SDs, which implies that X is smaller or equal to the value of the wealth associated with X0 and strategy Z. And X at time capital T, it gives this, and at time capital T, Xt is equal to eta. And so X0 allows the seller to be hedged, and so we obtain the other inequality. And since we had the other one, we have the equality between X0 and V0, which was the desired equality. Note that since X0 is equal to V0, here X0 is equal to V0, so we have that eta is smaller or equal to the value process associated to the superhedging price V0 and to the strategy Z at time capital T. That is, we can say that this strategy, initial was V0 and risky asset strategy Z, is a super strategy for our European option. Well, this is another characterization of the superhedging price V0 via constraint BSD. Well, to simplify here, we suppose that beta is equal to 0. Here, beta is equal to 0, but the filtration remains the same one, the big one, G, so the market is still incomplete. Actually, the optional process H can be decomposed as follows. That is, there exists a predictable process K, square integrable, and a predictable CAD-lag non-decreasing process A, such that HT is equal to AT minus the integral of K with respect to M. If we replace dm by its value, we obtain this equality. Since H is non-decreasing, well, the jump of H at the default time theta, which is just given by minus k at time theta, must be greater or equal to 0. And moreover, the other process here, AT, A plus the integral of ks lambda SDS, is also non-decreasing, must be non-decreasing. So recall that we had the following decomposition of the value process, nonlinear optional decomposition of the process X, of the value process X, replacing H by this decomposition, A minus the integral of K with respect to dm, we obtain this dynamics for X. Here dh minus dh is replaced with respect back this. And we have the two following the constraints. The first one we had seen here, which correspond to the fact that the jump of X at time theta, the default time theta, must be smaller or equal to 0. And also A plus the integral of case lambda s must be non-decreasing. So we have this property. We have shown that there exists zk, predictable and square integrable, and a predict non-decreasing process CAD-lag A, with A0 equal to 0, such that X Ka satisfies this backward equation. Actually, we can say that XZK is a super solution of this constraint BSD with default, and that is with these two constraints. Okay? We have no constraint, it will be a classical, a classical BSD, and here we have these two additional constraints which come from the incompleteness of the market. Note that this, if there was not this, the second constraint, this type of constraint BSD appears in the previous literature in a paper by Karoubi and Fay, which studies the super solution of a constraint BSD, well, not with default, but with jumps, Poisson jumps, and with non-negative jumps. Here we have just an additional process. Well, in their paper, they had shown the existence of a super solution of this constraint BSD, only with constraint Y, by a different approach, more precisely, a penalized method. Look here, we have another approach, and also we have a dual representation of the solution. So as seen, recalls what we had seen in the previous slide, that the super hedging price is equal to the initial value of the super solution of this constraint BSD. So this gives a characterization, since X is the minimal super solution. Well, recall the dual representation of V0. We have the following property. The supremum is attained if and only if the value of the process associated with V0Z at time capital T is equal to eta, almost surely, and it is also equivalent to the fact that the option is replicable. Well, when the option is not replicable, we know that there exists a minimizing sequence, maximizing sequence of Heron martingale probabilities Qn, such that V0 is the limit when n tends to plus l'infini of the Qn Heron expectation of eta. But we can construct a more interesting sequence, minimizing sequence. That is, we can show that there exists a sequence Qn belonging to round Q, such that V0 is the limit of the Qn Heron expectation of eta, and such that Qn converges to a non-negative measure Qn, absolutely continuous with P, in a weakly sense, as n tends to plus infini, and eta is equal to the terminal value of the wealth associated with the strategy V0Z, Q equal almost surely. Recall that Z comes from the nonlinear optional decomposition. So here Qn converges to Q weakly means is in the sense that the density of Qn converges almost surely to the density of Q star. Does I have a bit minutes only?
No, two.
Two, thank you. So in the linear case, we have an analogous result, and we can even say that V0 is the mean of eta under R star, where R star is also a limit of martingale probability measures. But of course, we cannot say something like that with backwards. So, voilà. Alors, for the buyer, by symmetry, we have this representation of the buyer's super hedging price. Well, I just wanted to show what happens with an American option. Well, the seller's superhedging price is defined as usual. Here we have a payoff xi. Well, here which is not necessarily right continuous. And the pricing hedging duality theorem is written as a mixed control optimal stopping problem, where the supremum is taken over all E-round E-round probability measures and over all stopping time tau of the expectation under Q of xi tau. And we have also, when beta is equal to 0, the following characterization via a constraint reflected BSD, reflected by the payoff xi t. And here, as the payoff xi t is not right continuous, we have this additional process C, which is CAD-lag optional, but here it's a left limit of C. And so the jump of C corresponds to the jump the jump of C the jumps of C correspond to the right jumps of Y. We have the same constraint as before, and we have also a square condition satisfies that this process C, and that is, it jumps only when Y is equal to xi. And it's also, so this type, if the market is complete, we have not these two constraints. Well, Klimziak will give a talk on Thursday, I think, or Friday, and he will speak about this type of equation, but without this constraint. For the buyer, right, we have this, it corresponds the buyer to the value of a game problem. Voilà. In the case when the process, the payoff process is CAD-lag and left USC, and there exists a superhedge for the buyer. So we stop. Thank you very much for your.
Yeah, thank you for. Yeah, thanks for a very elegant and clear talk. Any questions? Yuri?
I have an impression that even non-linear. Sorry. I have an impression that non-linear optional decomposition can be proven in larger, more general setting than here. Because
yes, of course. Yes. We had focus on
trivial
this
remark. If you take attentive look on backward stochastic equations, which are hidden here, this setting is based on, roughly speaking, martingale representational theorem. But the initial idea by Bismuth was actually more not about martingale representation, but Kunita-Watanabe decomposition. So maybe one can write it in more general setting.
Yes, there would be an orthogonal martingale.
Thank you.
In the equation, yes. It's, we have also backward with default in general filtration, and in this case, there is an additional martingale, which is orthogonal to W and M. Yes.
Okay.
But the driver F depends only on Z and K, a priori.
Any more questions? So how do we make the Zoom people come in? Do they hear what we are saying now? Yeah, so are there any questions from outside? This does not seem to be the case. Then once again, many thanks.
Thank you. Thank you very much.